Welcome, everyone. Thank you for coming to this seminar. So I'll start by saying a few things about myself first. My name is Jad. I'm currently a first-year PhD student here at the Tartu Observatory. I'm working in the cosmology department with Dr. Antti and Ilha. So today I'd like to present to you what I've done during my master thesis. So I did my master in theoretical and observational astronomy at the University of Groningen, where I was supervised by Professor Wim van de Weehaert. Okay, so as you can see from the title, my topic had to do with cosmic voids, and specifically what is their environmental influence on the development of dark matter halos. Okay, so the first question is, what exactly is my thesis objective here? And to answer this question, I want you to have a look at the figure on the right. This is where you can see the SDSS galaxy distribution map. So you will notice that each galaxy, the galaxies trace a pattern that resembles a spider's web. This is what has been coined in the literature as the cosmic web. So you see long strands of filaments stretching across the sky, connecting nodes in between. And you also can see these dark patches. These are the so-called cosmic voids. So, as you may assume, what voids are low-density regions in the universe, and they're ideal for the study of dark matter halos and their evolution of dark matter halos and galaxies. So, I had two goals in this thesis. The first goal was to describe the void environment, to see what the void sizes are, what are their shapes and profiles. The second goal was to investigate how the properties of void halos vary in comparison with the overall halo population.
What do you call a void halo?
A void halo? I will get there, but it's a halo located inside a void. Okay, I'll get there. Okay, so I mentioned already a reason why voids are important, but what other reasons are there? Because maybe one says that they're just empty patches in the universe, why bother study them? But they're actually an essential feature of the cosmic web. They occupy more than 70% of the volume in the universe. They span sizes between 20 to 50 megaparsecs. And in this plot, you can see one of the earliest voids discovered. It was in 1981 by Kirchner, and this is a void called the Butes void, which has a size of 60 megaparsecs, so quite one of the largest. Voids also act as organizing elements in the cosmic web, in the sense that they expand and they push matter outwards. I will come back to that later. They also represent excellent cosmological probes because they can help us understand structure growth, give us an insight into the dark energy parameter omega, and restrict the neutrino mass. Okay, but how do voids form and evolve, I ask? And they actually form from the underdensity fluctuations in the primordial density field. So voids experience a repulsive gravitational force. Or in other words, the surrounding overdense regions, they attract matter from within the void, and this will lead to a matter evacuation. At the same time, the universe expands, so voids will undergo super Hubble flow expansion. They will expand faster than the average expansion rate in the universe. So in the right plot, you can see a toy model. This is a model which describes an isolated spherical void. So here you can see the density profile as a function of the void radius. So notice that as time moves on, the density.
Just one second.
Yeah.
The super Hubble flow is the sum of these two things.
Yes, it's a result of these two things. Yeah.
May I ask again, when you see voids or underdensity, or do you pick some threshold density for that underdensity?
What would you want?
The same question what Maria asked, how to define void?
Yes, so voids usually are defined as underdensities in the sense they represent, in literature, usually they're defined as having 20% of the average density in the universe. However, when you try to identify them in surveys or simulations, usually a lot of algorithms have been developed, but I will get to there as well.
20% less.
20% of the average density.
Yes.
Yeah, usually they're negative. So this is what I'm getting at. So you can see that the density profile for this model of a void becomes more and more negative as time proceeds. At the same time, you can see the formation of a ridge, which becomes more and more dense as time proceeds. So the void pushes matter outwards, and it evacuates at the same time, forming this overdense ridge around it. So, yeah.
Sorry, 20% density, it is at the center of void. As you go away from the center, then
It
density
will start
increases.
increasing, yeah.
Yeah, so 0.2 mean density is the cutoff for the center, not for the overall void.
Yeah, you're correct, yeah, that's it. I will also talk about density profiles in my results. So in theory, a void forms when the event of shell crossing occurs. So essentially this happens when shells of matter which are located within the void will start expanding, will start overtaking shells of matter located close to the ridge. So when this happens, voids usually enter a non-linear growth regime and the expansion of them slow down. So usually the voids in surveys are considered to have reached this shell crossing state, so to speak, or level. Another important property of the void environment is their dynamics. So in 1993, Van de Weeghart and Van Kampen made a study regarding the dynamics and structure of underdense regions in different cosmological scenarios. And in this plot, you can see the radial velocity of a large void in a lambda cold dark matter simulation as a function of the void radius. So notice that in the inside of the void, from 0 up to 10 megaparsecs, the velocity increases nearly linearly. This is an indication of the expansion of the void. Then it reaches a peak, and then it starts declining again. As you go farther and farther from the void center, you will start encountering the high density regions. At the same time, they made a comparison with the predictions made by the linear theory and predictions made by the spherical outflow model, which represents an extension in the nonlinear growth regime. And you can see that the linear theory predictions don't really match the radial velocity profile, but when you apply the spherical outflow model, it actually starts to go pretty well, up to some radius. Afterward, they start diverging, and this has been associated usually with the presence of other overdense structures in that region. Okay, another property relevant to the voids is shape. So you may wonder, how do these things look like? So as you see in the SDSS galaxy distribution, they tend to be very irregular in shape. So to understand their shapes, one model is the ellipsoidal model used to approximate their shapes. So if you look at the right plot, you can see the axis ratios of the ellipsoids used to fit the voids. This is again in a dark matter simulation. So you'll notice that the void population tends to be slightly more prolate rather than oblate. So the ellipsoids tend to be more prolate. A strong influence on the void shapes is the external tidal field of the surrounding structure, and the acceleration that occurs on one of the void ellipsoid axes is given by this equation. Now, what is important are these three parameters that govern the equations, which is delta, the density, tau m, which is the tidal share of the surrounding tidal field, and lambda, which represents the dark energy parameter. Recall that I mentioned that the void shapes are very sensitive to this parameter lambda, and you can infer information about them. However, voids are limited to a density of less than 1, but the tidal share parameter has no upper limit. So this will generate usually a great deal of deformation in the void shapes. They will start departing from a perfect sphere. So I mentioned also that some simple properties of voids can be understood by the spherical isolated model or the ellipsoidal model. However, this is not entirely correct because voids are not isolated structures. They interact with the surrounding medium and with their peers. So this has been called in literature the void hierarchy, and is governed by two processes. The first process is void merging, while the second one is the void collapse. In the void merging scenario, imagine you have small voids which are embedded in a larger underdensity, so a larger void. If you look in the top three panels, you can see how this process occurs. So you have small voids which will start expand and merge together, while the matter which is situated in between them, the filaments, will start being squeezed out around the resulting central void and in the most right panel. The second process is the void collapse. So in this scenario, you have voids located in an an overdensity, which will start collapsing around them, as you can see in the bottom three panels. So in this case, the voids located in the collapsing overdensity will be squeezed out of existence. Naturally, this will generate a cutoff of small voids. So the voids which will be smaller than a certain radii will start to disappear as the collapsing overdensities will overtake them. Okay, what are some processes of what are some effects of voids on dark matter halos and galaxies? So, because voids are underdense, there will exist a lack of galaxy evolution processes, such as tidal stripping, quenching, and merging, for example. So, galaxies within voids will be at a more primitive stage of evolution. They will be more young. So, some studies have already shown that galaxies within voids will tend to be more blue, less luminous. The spiral galaxy identified also present a higher star formation rate. They also observed a lack of early types. Other studies have indicated that the void galaxies are gas-rich, and then they are smaller in sizes and they present lower masses. However, the halos within voids have also been So in regards to the void halos, cosmological simulations have also shown that they depend strongly on environment. And this perhaps would be useful to retain because you can have some expectations about my own results later. So it has been shown in the literature that the halos within voids present a lower mass and they also spin more slowly. Their shape is also affected. They tend to be more anisotropic. They are more deformed. It also, perhaps pretty obvious, is that they also present a lower abundance than their counterparts in higher density regions.
Just one question.
Yeah.
All these properties from halos and voids are derived from simulations or from observations?
Regarding the halos within voids,
Yes.
these are from simulations.
Okay.
Yeah.
And it's n-body simulations or hydrodynamical simulations?
I think it's usually n-body simulations.
So only dark matter is simulated.
Yes, I think so. Yeah.
Because normally in dark matter only simulations, halos are more anisotropic, and when you enter the baryons or you put in the baryons, it makes it more isotropic. So
But
maybe here.
this is a comparison between environments. Like you compare the halos within voids and with the halos in another denser.
If it was known that baryons inside halos made the halos itself more isotropic, then you are not, I don't know. Okay, so if you have dark matter only simulation and you compare the halos in one.
Yeah. Okay.
Thank you.
I would like to ask why elliptic galaxies don't exist in this list.
Why ellipticals lack in voids usually?
Yes.
Well, as I mentioned, the galaxies that are in the voids, because they're under dense regions, they tend to evolve more slowly. Usually elliptical galaxies form from collision of other spiral galaxies, for example. So usually have an abundance of spiral galaxies and blue galaxies, but very few late type very few early type galaxies because they haven't had the time to develop.
Oh, yes.
Okay, so now that I mentioned the void theory, I would like to move on and discuss the tools that I have used to perform my analysis. So we know that structure formation, which leads to the formation of the cosmic web, depends strongly on gravity. And in order to simulate the structure growth, we use n-body simulations. In this work, I use the Gadget 2 n-body code, which, without going into many details, uses a 3PM algorithm, which in order to compute the gravitational forces between particles. At the end, you're left, not your left. At the end, you have a particle distribution which has positions and velocities. However, this is a discrete sample, and it may produce inaccuracies in the analysis. So you would like to have a continuous volume covering reconstruction of the density field. So to achieve this, we use the Delaney tessellation. One option is to use the Delaney tessellation field estimator. So the idea of the DTFE is that it uses Delaney tessellation to reconstruct the underlying density field from a particle distribution. One advantage of using this algorithm is that it maintains the hierarchical nature of structure formation. And in the right plot here, you can see a slice of the density field from the gadget simulation. And by visually inspecting, you already can notice that the apparent elements of the cosmic web, such as the filaments, clusters, and of course the dark patches representing the voids. Okay, so now that we have our density field, we want to identify voids within them. However, it is not fully agreed how do you define the void. So various algorithms have appeared. Kohlberg et al. In 2008 actually made a very good review of the existing algorithms. But in this work, I used the watershed void finder. And this is based on the watershed transform, an operation which stems from the mathematical morphology, usually used in segmentation of images. And to understand this algorithm, you can imagine a geophysical landscape as the one here on the right. So this landscape has various peaks, basins, and ridges. And you can imagine next that you are filling with water this landscape. And as the water grows slowly, you'll have all the landscape submerged. And what you notice is that the basins are now separated in between them by the high altitude ridges. So you may see how this perhaps translates to the cosmic web, because basins represent regions of low density, so our voids in this case, while the peaks and ridges represent regions of high density, the filaments and the superclusters. So this is why I want to go. Yeah, okay. Here you can see an application of the watershed void finder in the Gadget 2 simulation. So you can notice that we have the void patches identified by the algorithm. The colors are not correlated with anything. They're just to show the variety of the voids. You can already see that they are very irregular in shapes. And I also see here, I show you here a 3D representation on one of the voids in the simulation.
Was there any threshold cut given to identify voids, or you just took whatever?
In the detection of the voids.
Yeah.
If there was any threshold, let me think for it. No, I don't think I put any threshold for the watershed. Why are you asking?
Sorry.
Why are you asking?
Because depending on the threshold, you will have different kinds of voids. Like if you go back to your previous slide.
Yeah, this one.
So yeah, if you lower down the level,
yeah,
then you will have different ridges. Because if you level up, then at a certain level, everything would be merged together and would give you just one void.
Yeah, you have a different population of voids depending on threshold. Yeah, that's true. Actually, will have to remember because it's been already 1 year and a half. But yeah, I don't recall the threshold. Yeah, I'll come back to you. Okay, so we have our voids now. We would like to identify the halos. And for this, we use the Logstar Halo Finder. This is an algorithm developed by Behroozi in 2013, which is based on a variant of the Friends of Ferns. So in the original Friends of Ferns, you have particles that are grouped together within a certain linking length. In this variant, the Logstar basically merges already made groups by the original Friends of Ferns together if they are within a certain larger linking length, from what I understand at least. Afterwards, the algorithm builds a Friends of Friends hierarchy. It tries to progressively reduce the length such that only a fraction of particles will be present in each subgroup. Afterwards, the Friends of Friends subgroups are converted into halos. So at the end, you essentially have the halos and their properties. You have positions, velocities, spin, shapes, and so on, which you can analyze.
Let me understand. A Logstar only uses positions or also uses velocities?
At the end, you're given from the particle distribution.
Yes, only the positions.
No, I think it uses the velocities as well.
Okay.
Yeah.
Couple.
Okay, so we also have the halos now in the simulation, but we want to identify halos within voids specifically. So for this, I wrote a Python script which computes the convex hull for each void in the simulation. So essentially, the convex hull represents the smallest polyhedra that encloses an arbitrary point distribution. I like to think of it in the following way: like if you have a collection of pencils that are perpendicular on a table, randomly distributed, and you stretch a rubber band around them, the convex hull represents the outer boundary region. So this is an image that shows the convex hull, the gray polyhedra, for one of the voids in the simulation, while the halos have been identified by simply requiring that their positions are located within the convex hull boundary. You can already notice that the majority of the halos are located more on the boundary of the void and maybe very few in the center.
So you identify halos in two different ways. One with the convex hull and another with the
No, I didn't define the halos differently. The halos are identified by Rockstar Halo Finder.
Okay.
I then computed the convex hull for each void. So I have the void boundaries. And then by using the positions of halos, I require them to be inside the boundary.
Okay.
But this polyhedron seems to have very few faces on it. Do
Yeah,
you
that's
want
true.
to constrain the number of faces it can have?
I couldn't control that, but probably there's surely a way you can do that, but I couldn't at that time at least.
So what did you take to construct this convex hull? What input?
What input? It's just the void positions. If you have their XYZ positions, you can construct the convex hull from it, basically.
But void, say this is one void, suppose.
Yeah.
Then for convex hull, you need some collection of points.
Yes.
But for one void, you will have only one data point. So how do you?
Wait, what do you mean for one void? You have only one data point. For one void, you have all the elements that construct the volume of the void. Like you have all the XYZ coordinates of that void specifically.
So that is, you are taking that from the grid information, the DTF.
Yes, what watershed void finder gives you that after you applied it on the density field. It gives you every position of the void volume element.
So why? Okay. Then
Because it's harder to compute to take the boundary only from the XYZ coordinates than construct the convex hull.
No, but if you already have those values, the grid points or voxels where you have, you know that these are void. These are part of the void. Then
Yes.
why do you need to use convex hull? You already know that you have already identified your void.
Yes, you identify them, but the volume elements that you have in your data don't give you, they give you the boundary, but you have to specifically find exactly those elements surrounding on the whole void, and that is not a trivial procedure to find. At least I couldn't do it easily. This is like an approximation of that boundary.
Okay.
Yeah. Okay, other questions? Okay. Okay, and now results finally. So there are two ways. So I mentioned that first I wanted to look at the void environment and then to look at the halos located within voids and investigate if they differ somehow than the overall halo population in the simulation. So I start by describing the void environment, and you can compute. A first property you want to look at is the void sizes, and you can do this in two different ways. First, you can compute the equivalent radius. This is the radius that corresponds to a sphere which has the same volume as the volume of the void. And if we plot the equivalent radii for all the voids in the simulation, you get the top two plots. And you can notice that they span sizes between 5 and 22 megaparsecs, with an average of around 11 megaparsecs. However, we have seen already that voids are volumes that differ a lot from perfect geometrical objects. So they have very irregular boundaries. So in order to perhaps have a better estimation of their sizes is to compute the boundary to center distance. So you have your convex hull and you take the center of the void, and then you compute the average boundary to center distances. And if you plot this in the bottom plot, you get that the voids in this case now span sizes between 5 and 35 megaparsecs. So the interval is now larger. The average now is about 17 megaparsecs. So it's a better approximation of the void shapes than by using pure spheres or considering that they are spheres. So the next property is the void shapes. And as I mentioned, there are two different ways here you can do this. One is to fit them with ellipsoids by computing the shape tensor. The eigenvalues of this shape tensor will give you the axis of the ellipsoids. If you plot the ratios of these axes, you get the top plot. So you can see here is plotted C over A by P over A. And you can notice that the population of voids here is slightly squished towards the central diagonal. So they tend to adopt a more prolate shape, as we have seen previously in the theory. The bottom plots show two different voids. This one here, it's supposed to be a more spherical void, while with the axis ratios closer to 1. While this one here, it's supposed to be a very deformed anisotropic void. So they can have.
Prolate is a lengthening. I'm always confused on what is prolate and what is oblate. Prolate is a lengthening and oblate is a rugby ball, or is the other way around?
So prolate means that the B axis of the ellipsoid is larger than the C, I think. Yeah. Yeah, I confuse them as well sometimes. One of the axes is larger than the other one.
Yeah, that is always the case.
Yeah.
Maria, prolate is like sausage and oblate is like the plate.
Yeah.
And the rugby ball is the
Yeah.
prolate.
Yeah.
That's a better way. That's actually a good way to remember.
Think of rugby ball.
Yeah. Okay, so by this method, you find also that voids tend to be more prolate. I also wanted to check if there's any dependence between the sizes of voids and their shapes. So we can compute the form factor, which takes into account the volume and the area of the void. So if you plot the volume and the area of the void ellipsoids and plot the form factor against the size of the void, the radius, you get the top plot. So notice here that, oh, I forgot to mention what are the blue and red things. So I divided the population into two based on their sizes. I gave the name population of small voids in blue and a population of big voids in red. This is purely arbitrary, just to see if there's a pattern. So you can notice that in this case, when we use the void ellipsoids, there's no there's no pattern between the shape and their sizes. However, if we put instead of the volume and area of the ellipsoid, if we put instead the volume and area for the convex hull, we get the bottom plot. And you can see now that there's a pattern. So larger voids tend to be slightly more spherical than their smaller counterparts. And this has to do with the fact that as time moves on, voids tend to expand more and more, and they tend to become, in their interiors at least, more spherical. So we also want to have a look at the interior matter content. And you can do this by computing the radial density profile. So these four plots show the density as a function of the void radius. So you can notice that the inside of the void up to approximately 1 characteristic size, that is the average void size, the density profile is mostly flat. So the void is mostly empty inside, as you would expect, and as we have seen in the spherical isolated model. As you go to further and further distance from the void center, the matter starts increasing abruptly. And if you're wondering why the spikes appear, it's probably the presence of substructure within voids. So we have mentioned that the watershed void finder preserves the hierarchy of structure formation. The right plot shows the average density profile for a number of 800 voids in the simulation. So now the most substructure has been averaged out. However, there is a bump at around 1 characteristic void size, and I think that it's also caused by the presence of substructure, but I haven't had full time to look into it. The dotted line represents the density contrast, and I computed this in order to see how the density profile computed by me deviates from a perfect spherically symmetric distribution. And you can see that the two profiles more or less are the same in the interior of the void. However, as you depart from the void center and you approach the boundary, the two profiles starts diverging, indicating that the density starts being it starts deviating from a perfect spherical symmetry distribution, basically, because you have the presence of the high density regions surrounding the void.
Why do you have the divergence in the inner parts for some of the of the voids?
Why the divergence here?
Yes.
Yeah, good question. Well, I imagine because, well, first of all, the divergence is quite small, but why it appears?
It's a factor of 2
In what case?
in all the cases. No, in the ones that are in the middle.
The
These
four,
four that.
I think it's a factor.
And maybe a little less.
Yeah.
When you are plotting these density graphs, are you just taking the halos or the density field? which
Density
are, just okay, within the void, or you are taking just from the center, you have this entire field and you are taking the concentric shells and then.
Yes, I'm taking concentric shells, basically. So I'm going measuring the density field from outer and outer spherical shells from the center.
Then shouldn't it fall back to the mean density field? So delta equal to the mean. So it should be around 0 at some point after, say, 3 or.
I think you're right, but I cut it the other parts.
Okay.
Yeah. But I think you're right. They should.
And the peaks are galaxies. So I
Peaks
have
are-
my void,
Yeah.
then there are galaxies in there.
Yeah, they're superclusters or filaments probably, but I didn't study them. I was interested in the void specifically. But yeah, they're high density regions.
Okay, yeah.
Okay. Okay, so another property is the dynamics of the voids. And as I mentioned earlier, they act as an organizing element because they push matter outwards from within their interiors. So in the left panel, I show again a slice of the density field identified by the DTFE. The middle panel shows the velocity field. So here the dark blue patches correspond to the regions of low density in the left panel, while the green regions correspond to regions of high density. So basically we have low velocity and high velocity. And you cannot, the arrows represent the velocity stream. Well, I'm not sure you can see the arrows from where they start, but usually they start from the center of the void, for example, and they go outwards, indicating that the void tends to expand and to push matter towards their boundaries. And the right part, I just inputted some of the voids in the simulation just to see how the velocity stream basically is shown. Okay, if we want to take a closer look at the velocity profiles and compare them with the predictions made by the linear theory, we can have a look at the columns here. So the left column shows 4 examples of voids in the simulation. The white pixels shows the density field, so you can see that they have the surrounding ridges. The arrows represent again the velocity stream. The middle panel shows the density profiles for these corresponding voids, while the right panel shows the velocity, the radial velocity profile with a continuous blue line. So in the interior of the void, the velocity seems to increase, mostly linear, and then it's followed by an abrupt increase. If we compare this with the predictions made by linear theory, which is the dotted line, well, these don't fully correspond. Like the predictions made by linear theory peak way earlier and usually have higher amplitudes. This is something I didn't have time to look into, but it would be interesting to see why they deviate that much, perhaps because voids are in a very nonlinear regime, or maybe indication of the void hierarchy, but I have no clue, honestly. I don't know at the moment why they behave like this. Yeah, if anyone has an idea.
You were saying that it seems like it deviates in the parts where you have over densities, which is the highly nonlinear.
Well, they
So
seem
it's
to,
what you are saying, no?
yeah, well, they seem to deviate mostly. Well,
So when
towards
you
the
have
end
the,
where the
when you
dot
have the
corresponds.
peaks, when you have the peaks in the density field.
Yeah, but they don't correspond neither with the low parts of low density parts in the void. Like they're completely deviated. That's, yeah, I couldn't exactly figure out why that happens. Yeah, if anyone has an idea, you can tell me.
Back in the code.
Yeah, maybe.
That's how.
Yeah, it was weird anyhow, I don't know. Okay. And now we finally reach the void halos. So I showcase here the overall halo population identified in the simulation. And you can notice already it forms the familiar cosmic web. The right image shows a slice of the density field, as we have seen earlier. The yellow points represent halos identified within the simulation. You can notice already that they don't really are many halos within voids. Most of them are concentrated in filaments or in the nodes part of the web. So let's take a look at the population for now. So I identify initially 75% of halos to be located within voids. And if you take a look at the right figure, you can see the number of halos as a function of distance. With blue, I show the distance from the void boundary, while with orange, I show the distance from the void center. So there's two kinds of distances we're trying to see here. The perpendicular line shows the characteristic void size, so the average void size of 17 megaparsecs. So you can notice that the majority of void halos are located within the boundary. And as you depart from the boundary, or as you go farther from the center, it starts. If you depart from the boundary, they start decreasing. And if you start going from the center outwards, they start increasing. However, it cannot be that 75% of halos to be located within voids. That's a way too much higher percentage. And in the literature, it has been found that around 10 to 11% are located there. So something had to go wrong. And it seems like the watershed void finder identifies the void boundaries as high density regions. So in order to correct for this effect, I only consider the halos that are located at a distance from the boundary equal to the characteristic void size in order to reduce the sample data and to only try to get the halos which are more deeper in and not to be located on the void boundary. So after inputting this criteria, we get that we have only 10.6% of halos to be located within voids. So we can also quantify the abundance of halos by taking a look at the halo mass function. So the halo mass function represents the number density of halos per logarithmic mass bin. And it's usually characterized by power law at low masses and an exponential cutoff at higher masses. So if you plot the halo mass function for the void halos shown in blue and for the overall halo population shown in gray, you can already notice that void halos tend to be lower in abundance and also they present a lower mass. And if you ask why, well, it's because voids are underdense regions. By definition, they prohibit the formation of halos, which are more massive. If we look now at the halo shapes, we can understand the shapes by fitting them with ellipsoids. Surprise, surprise. So if you plot the axis ratios of the void halos in blue and for the overall population, you will notice that there is not much of a distinction actually. There is a very slight difference between the two distributions, with the void halos appearing slightly anisotropic. Now, if this effect is real or not, maybe it would be better to investigate it in higher resolution simulations. So if we try to understand this systematically, I take the average axis ratios for the void halos and plot them against the distance from the void boundary shown in blue and from the void center shown in orange. So if you depart from the void boundary and you go deeper and deeper into the void, you will notice that the axis ratio starts decreasing. So it seems like void halos tend to be more flatter in their appearance. However, afterwards, after you reach the characteristic void size, this trend starts increasing. Why this happens is maybe perhaps the low number of halos located deeper into the void, which may cause the presence of spikes. But this is something again which has to be better investigated, because yeah, this is a weird trend and surprising to me as well why they appear like this. But yeah, sorry. And the final property that I investigated is the halo spin. So this is important because it quantifies the importance of angular momentum in the overall over the random motion. And it can be described by the bullet parameter lambda. So if halos have a higher lambda, then this means that they are supported rotationally. If they have a lower lambda, it seems they are supported more by random motions. So if you plot lambda as a function of the halo mass, again, for the void halos in blue and for the overall population in gray, you can notice that for constant masses, the void halos tend to spin slightly more slowly than their overall counterparts. If we take a look at this trend systematically again by plotting the average lambda as a function of distance from the void boundary from the void center, you'll notice that as you go again deeper from the void boundary and you approach the void, as you go and you approach the void center, the halos will spin more and more slowly. Same with the mass, but this we already seen this effect in the halo mass function, I guess. As you go to the closer, if you go closer to the void center, you will encounter halos with lower mass. And if you ask why void halos should spin more slowly than their overall counterparts, this has to do with the way halos acquire angular momentum. And this is explained by tidal torque theory. And the idea is that protohalos accumulate spin or angular momentum if they in the linear growth. So in the linear regime, they slowly grow and they increase their angular momentum. Another factor, I think, is the halo merging, which also contributes to an increase in angular momentum. However, because voids are not or are under dense regions, you're not be able to grow your halos as much, and you also have a lower probability for their encounters. So there will be a lot of halo merging as well. But this is something that again has to be studied, and I haven't looked into it too much. And to conclude, the main point of this thesis was to investigate the void environment and to see how the halos within voids are affected. And the results can be divided into two chapters. Chapter 1 basically describes the void environment. So I found that voids have a characteristic size of 17 megaparsecs. They have more prolate shapes, and the larger voids tend to be more round. I also look at the interior matter content of voids, and they tend to present underdense interiors and high density boundaries. The dynamics also indicated that matter flows outward from the inside of the void, and that the velocity profiles tend to have a linear increase from the center of the void towards the boundary, which corresponds to the flat density profile. The void halos, which is the chapter 2 of the thesis of the results, is that I found that the halo abundance presents approximately 11% of halos to be located within voids. The halo mass function indicates that the void halos usually tend to be lower in mass than the overall halo population, and their shapes and their spin, the void halos tend to adopt a more flattened shape and to spin more slowly than the halos located in other environments. And some perspectives which perhaps may be useful to get better results is that we can use higher resolution simulations like Illustris or Quixote. We can perhaps also study the time evolution of the void halo properties. You can check other redshifts and see if the properties also have a similar trend. And also, since I really am insistent of getting to approximate the void boundaries as ideally as possible, we can use a better algorithm to constrain them. And that is it. Yes. Thank you. If there are
questions, comments, please. Those who are watching the stream can also just speak up or write some questions to the chat.
Yes.
I would like to ask about observational observational evidence existing of voids,
Yes.
and in which epoch of Big Bang began formation of voids.
The void started to exist ever since the density fluctuations themselves started to manifest in the primordial density field. So we know that we have the density field, density fluctuations appeared in the field, and it is associated with the presence of quantum noise. This is what I understand, and is that is accepted. And from these density fluctuations, you will start having structures that grow, and as these matter points start accumulating, you'll also be left behind these low density regions. So this is when voids start growing.
Are voids actually quantum fields?
I cannot respond to that question. I don't know. But if you say there are quantum fields, then anything is a quantum field. The structure itself grew through density perturbation.
And how relation between dark energy and voids?
Sorry?
Dark energy and voids, the relation between dark energy and
Oh yeah. So I showed here that the void shapes, if you approximate it with ellipsoids, is dependent on the dark energy parameter lambda.
lambda.
So you can get an insight into this parameter if you analyze their shapes.
A cosmological constant.
Yes.
Thank you.
Yeah, the seeds of voids are there from the beginning, but of course they take time to manifest them.
Yes.
Anna?
Well, did I understand it correctly that all this analysis of shapes and everything is based on simulational data, not observational?
No, this is pure simulation.
Oh,
Yes, but there are studies who investigate the shapes of voids and abundances on surveys.
okay, then I can ask if do you intend to try your methods on like observational data, or it's
That's actually what we're doing. Yeah, in this PhD project, this is what we want to test. Yes,
okay? Thanks.
yes.
So I didn't understand. So at the beginning, you said that you identify like 96% of halos within voids.
75, yeah.
Also, okay, 75. And then you said this is not correct because it's not what has been found previously.
Yes. No, initially I said that so this algorithm that identifies voids identifies also the boundaries of voids by high density regions, the filaments and clusters. So when you make this measurement of halos within voids, you also gather like the innermost boundary region of the void. So you have to account for that. This is why I impose this criteria, which basically tries to accumulate only the halos that are located into the deeper side of the void.
But I didn't understand what is the criteria that you are in order to go to 75 to 10 points.
So I only selected the halos which are located within a distance of the characteristic void size, which is the average size of the void.
This 17 kilo.
Yes.
Pascal.
Yes.
But you also were saying before that it was a bit simplistic, the shape of the cluster with the convex hull.
Sorry. And the
So
second part,
the shape of the cluster is given by the convex hull.
the shape of the void is
The shape of the void is given
Yeah.
by the convex hull.
yes.
And before you were discussing and saying that it was a bit maybe simplistic.
Oh, if
So-
it wasn't clear, sorry, I'm taking the distance from the void boundary as it's given by the convex hull. So you can have the convex hull basically can give you the void boundary, but at the same time, you have the void boundary, well, as it is identified by the watershed void finder, but that is not correct because it includes also higher density parts in the web, if that makes sense.
Is it like just a piece of a boundary is included in something
Yes,
like
so
that?
the way watershed, okay, maybe I should say how this algorithm identifies voids. So it searches first for the lowest density point in the density field. Next, it starts merging together regions, pixels in this case, let's say, that are around the lowest density point. And once it reaches a certain density value threshold, which is common for two basins, let's say you have two voids and you have the boundary between them. So once this algorithm reaches a certain common value that is located on the boundary, then it segments the voids, and that is what the voids are. Yeah.
Yeah, can you tell the density profile again?
Yes.
Wait, because at the moment, you're talking that, when it's still maximum, but you still pointed out that at some point it should go to the mean of the density. So at the moment, I don't know whether you are not doing far enough, or there is something wrong with the calculations, and just for the fix, if you know what to expect at far distances, then do that, your algorithm gives what we expect. But the other way how to calculate the density profile is just to take the distance from the convex hull boundary. And
Yes.
basically then you should see that there is some excess of matter at the boundary, and it drops if you go further away or if you go inside the way.
That's what I wanted to do, but I implemented the boundary pretty late, and I already had to present my thesis. But I also do that, like trying to investigate the density profile from the boundary, and this has been done by Hautun at some point in one of his papers, completed the density profile from the boundary, and was interesting in itself. But I think that's a better option actually than to measure the density profile from the center.
You can do the both,
Yes.
Yeah, true.
You kind of have to do the both because from the center you get like a cleaner picture in the center, and coming from the boundary inside.
Yeah,
You
exactly.
get, but if you go from the boundary to the center, or count your distance from the boundary, you will end up mess inside.
Yes.
Inside the void. So
Yeah. I agree.
combine them.
Yeah, I agree. It should be done both.
And also, you can take different bin sizes, the radii of different voids. Like say you plot the density profile of voids from say radii 10 megaparsec to 20 megaparsec, something like that. Oh, because bigger voids, they generally don't have this ridge feature in their density profile, and smaller voids. So you have kind of two kinds of voids.
Yeah.
Right.
Yes.
So you would be able to see that in the lower or smaller voids will give you this ridge, while the bigger ones, they will just slowly goes to the mean without giving you this
Okay.
density ridge.
Okay.
Otherwise, if you plot, say, if you stack and plot a single profile for all these voids, then these two would
Merge together.
yeah.
Average out. Yeah. Good.
And second thing, I guess for the 75%, if you put a cut of 0.8, the threshold cut of 80% of the mean density, 0.8 times the mean density, then you would be able to get that 10% halos within voids. Then you don't need to take a particular distance from the center plane.
Oh, okay. I mean, if you impose the density threshold from the start,
Yeah,
then
yeah.
yeah, that could be done. And you said that would be better, like do this.
In literature, many people take this 0.8 to identify voids,
Okay.
the interior regions at least.
Yeah. Yeah.
One of your results was that the halo spin in voids is lower than the usual spin, right? But you're only looking like at the dark matter only simulations, so there's no actually galaxy in there.
No.
But you also say that there's more spiral galaxies inside voids, right?
Yes.
I'm not sure how these two work together, but I would like expect that the spiral galaxy halos have higher spin, or does it work like that? But you find that they have lower spin, but more spiral galaxies.
Well, I haven't looked at galaxies. My point is to study the void halos. So you're saying spiral galaxies have higher spin usually?
I'm not sure. I'm not sure if it works like that.
Halo spin and galaxy spin are not, they are related, but there is not one-to-one relation.
And also about spiral galaxies, they are not so deep in the void. I mean, they are closer to void or is closer to planet. So if you look at morphology.
So in the center, they still have more elliptical galaxies?
No,
No,
but there are also irregular galaxies and
Okay,
more
yeah, of course, yeah.
Galaxy 2 is like.
That's true, yeah.
And if you go deeper in the void, it's different. So just for historical notice that we have a series of papers on void here, you know, from our looking to different types. And it's based on both of them.
What are others?
I had one last stupid question that I wasn't. On the second slide, you showed something interesting. Can you tell us something about the supervoids that is on there?
The second slide, this one.
Yeah, yeah. You can see two supervoids on the left and right side. Something about them.
But yeah, the lack of observation. Yeah.
Great Eastern and Western pizza voids. Merrily spent an hour here and enjoyed it. And we expect to enter again. And see you next week. Very likely for this semester, astronomy will be on Tuesdays at 2 o'clock.